Hello, ladies and gentlemen. Today we are going to take a look at some special skills that we need before we head on into our next unit, and that is an understanding of the Pythagorean theorem as well as special right triangles. Now, like I said, as we head into our next unit, some geometry skills are going to be very important. Understanding the Pythagorean theorem, understanding your special right triangles and their shortcut relationships, as well as your knowledge of how to use and apply the three basic trig ratios. For your notes today, you're going to maybe need a pen or a marker. A calculator is going to be important, and that square piece of paper, because we're going to be making this triangle toolbox. Okay, so we're going to make this as our end product on where we're going to keep these very important notes. The corners of the square piece of paper that you have there can be folded into the center, as you see, to make these four little triangular flaps for the triangle toolbox. Get it? Like it's made of triangles, but anyway. Okay, and on those four little flaps, you have the Pythagorean theorem, you have 30, 60, 90 special triangles. Another big tool that we're going to use is trigonometry, as well as our 45, 45, 90 degree special triangles. So these big four topics here are going to be hugely important in our next couple units, actually, as well as on the ACT, pre-calculus, any other math class or applied math that you might take after this. We'll definitely focus on this area of geometry as one of the biggest priorities. So this is a great place for us to summarize our notes. Underneath each of these flaps, we're going to write some formulas as well as an example. So you decide where you want to write the formula. If you want to write the formula on the top of the flap, and then underneath on the bottom portion in the square, have room for the example. But when you open up the flap, we need to have a formula as well as an example there. So let's first start with the Pythagorean theorem. The Pythagorean theorem can help you find a missing side of a right triangle when you're given the other two sides. This is the formula for the Pythagorean theorem. One of the most commonly used formulas outside of just generic math classes, okay, out in the real world, is this understanding of Pythagorean theorem and how it relates to right triangles. So in a right triangle, you're going to have a 90-degree corner. Always across from the 90-degree corner, the longest side is always going to be C, the hypotenuse. The other two sides, A and B, are just legs of that right triangle. So when we say we're talking about the Pythagorean theorem says one leg squared plus the other leg squared will equal the hypotenuse squared. So how do we use this to find missing sides? Well, let's use the Pythagorean theorem to find a missing side in this right triangle. So in this right triangle, the side that's missing is over here across from the 90-degree corner, and that would be the hypotenuse. So C is missing. The other two sides are the legs. So if I set up the Pythagorean theorem, a squared plus b squared equals c squared, a could be 4 squared, the other leg would be 8 squared, and the hypotenuse is c squared. So now if I actually square these numbers, 4 squared is 16, 8 squared is 64, that's c squared. 64 plus 16 is 80, so 80 is c squared. So now I would go ahead and square root both sides. So c would be the square root of 80, which I can break apart using a perfect square like 16 times 5. 4 also goes in there, but it's not the biggest perfect square. We want to make sure we use the biggest perfect square. So the square root of 16 is 4. The square root of 5 I'm going to leave alone. So the hypotenuse is 4 square roots of 5. Now, why didn't I put a plus or minus there? Because I took a square root. Well, you don't need a negative here because we're talking about the side of a triangle. So we don't have to worry as much about the plus or minus when we're focused on finding an application here, which is finding the side of a triangle, okay? So 4 square roots of 5 is how we would label that hypotenuse. Let's look at another example here. This one, you're not finding the hypotenuse. The hypotenuse is already given. The hypotenuse is across from the 90-degree corner. This is the hypotenuse. It's 15. We're going to use it to find a missing leg. So we again would use the Pythagorean theorem, a squared plus b squared equals c squared, 6 squared plus x squared, because 6 and x are the two legs of my triangle, and the hypotenuse is 15. So 6 squared is 36. X squared, 15 is 225 squared. Now if we go ahead and subtract the 36, we're going to have x squared equals 189. And now I square root, x would be the square root of 189. which simplifies by dividing out a 9 times the 21 here. X equals square root of 9 is 3, square root of 21, I don't know, it's irrational, cannot be found. There's my answer, okay? 3 square roots of 21. So we've used the Pythagorean theorem to find missing sides in right triangles. Now, another important fact that you should remember is 45, 45, 90-degree triangles. So underneath the 45, 45, 90-degree triangle flap, this is the whole idea of a formula you might want to write down, okay? On the formula spot or up in the corner, wherever you want to write your formulas, make sure you write this stuff down. This is a 45, 45, 90-degree triangle. It has two congruent legs, and it has one hypotenuse that is not the same. Now here's the deal with the 45, 45, 90. It's also called an isosceles right triangle because these two angles are both 45 degrees. Two congruent angles means you are going to have two congruent sides. So the sides across from them are the same length. Now they're not 45 because we're talking about degrees inside the triangle versus a length on the outside. But we do know that the legs are congruent. The angles are 45 and the legs will be congruent. Now when this happens, when people have studied 45, 45, 90-degree triangles and the relationships, they have found out that the hypotenuse is the same thing or equal to the leg times the square root of 2. So in a 45, 45, 90-degree triangle, we don't have to do the Pythagorean theorem and then simplify our square roots and all that stuff because we have this special relationship where the hypotenuse will equal the leg times the square root of 2. Now, how does this look when we try to solve one? Well, let's take a look at this. Make sure you have this formula down. This is the formula I'm going to be using. Here's a couple of examples for 45, 45, 90-degree triangles. It says find the exact value of x. That means we're not allowed to use decimal approximations here. These are 45, 45, 90-degree triangles. I can see the 90, I see the other 45, and if I subtract the degrees from 180, I know that this one would also be 45 degrees. Now, because they're two 45-degree angles, that means the legs are congruent in this triangle. So if this one's 8, so is this one. I could do the Pythagorean theorem to go ahead and solve, or I could use my understanding of this formula. The hypotenuse equals the leg times the square root of 2. Now in this case, the hypotenuse is labeled with an x, so I'm just going to go ahead and place the x where the hypotenuse is, and the leg is an 8 times square root of 2. Now x is already alone, so all I need to do is simplify this part. Well, x would just equal 8 square roots of 2. Done. I already know the hypotenuse because the hypotenuse is whatever the leg is, just times the square root of 2 behind it, okay? So now let's look at a second example. This one is a little bit tougher. We have the hypotenuse. We have an x on the legs. So we're going to use the same formula. Hypotenuse equals leg times the square root of 2. In our case, this time though, we have the hypotenuse of 10 equals the leg, I don't know, that's the x measurement, times square root of 2. Now notice in this example, x is not alone. So I would divide by the square root of 2 to get the x alone. They would cancel out over here, x would be alone, but on this side I'd have 10 divided by a square root of 2. Now this is okay, but you know what? We can't write a decimal answer, and you can't have a square root in the denominator of a fraction. So we're going to rationalize the denominator. That means multiply by the square root of 2 on both the top and the bottom because the square root of 2 is the thing we can't have. So on the top I would have 10 square roots of 2 over on the bottom when I multiply, that gives me a square root of 4, which is in fact just 2. So now I can simplify 10 divided by 2 is 5 square roots of 2. So I have x equals 5 square roots of 2 for the length of this leg up here. Okay, so using those formulas and then manipulating them using algebra, I mean, that's really what we're talking about here. Just remembering those formulas brings us back from that geometry knowledge. All right, and now let's look at our special 30, 60, 90-degree triangle. So 30, 60, 90-degree triangle looks like this. He does not have two congruent legs. He has a longer leg and a shorter leg and a hypotenuse. Now the shorter leg is always going to be across from the 30-degree angle because the 30-degree angle is open less, right? The 60-degree angle will always be across from the longer egg because it's open wider, so it's going to make a longer leg across from it. And the hypotenuse, no matter what, still always across from that 90-degree corner. So in this case, when you have a 30, 60, 90-degree triangle, they're a little bit more complicated because you don't have two congruent measurements. Because of that, we have a hypotenuse equals 2 times the short leg, and the long leg will equal the short leg times the square root of 3. Because we don't have two congruent measurements or two congruent sides in this case, we actually have two formulas because each leg is a different length. All right, so hypotenuse equals 2 times the short leg, and the long leg equals the short leg times the square root of 3. These are my two very important formulas to know, and also, formulas, spelling's nice, and also this picture kind of makes you remember what part matches with the long leg or the short leg. All right, now let's look at a couple examples here, and then we should be done. So here's one example. I have a 30, 60, 90-degree triangle. I can tell because I have a 30-degree angle in the corner, so that means this one is 60. And we have two pieces of missing information that we're trying to find. Now, we can use our special right triangles to find both. So if I have a 30-degree angle here, that means the only piece of information I actually know, look at that, the only piece of side length that I know is 4. 4 is across from the 30 degrees, so 4 is the short leg. Now I would need to use a formula there from my list of two formulas that deals with the short leg. Well, one of those formulas is that the hypotenuse equals 2 times the short leg. So if I just go ahead and plug in my measurements from my triangles here, my hypotenuse is x, 2 times, what's my short leg here? 4. So if I calculate 2 times 4 is just 8, it would say x equals 8. Well, that's easy. All right, I got my hypotenuse just like that. Now, the y that I'm looking for is on the long leg. So let's go ahead and use a formula for that. The long leg is equal to the short leg times the square root of 3. That's from our formula list. The long leg is y. The short leg is 4 times the square root of 3. So if I just simplify that, 4 times the square root of 3 is just 4 square roots of 3. So the y is 4 square roots of 3. Now let's look at this other example over here. Again, we have a 30, 60, 90-degree triangle. This time I'm given the hypotenuse. So I need to start with a fact about hypotenuse. The hypotenuse equals 2 times the short leg. So the hypotenuse in our case is 6. 2 times the short leg in our triangle would actually be the x. So now I have to solve for x on this one because x is not alone. I'm going to divide by 2 to get x alone. So x would equal 3. Now this piece right here is 3. Now when I try to find y is the long leg. The formula says long leg equals the short leg times the square root of 3. So my long leg is y. My short leg is x, which is 3 I just found, right? 3 square roots of 3. So if I simplify, y would equal 3 square roots of 3. So using our relationships or those special right triangle formulas can help us find these missing sides using no decimal values but exact values, and also just simple algebra manipulation, right? Just dividing or multiplying would give us those answers, okay? So we're going to look to use those special right triangles whenever we can. Here's one final example if you need a little bit more on how this works. It says find the missing side lengths below. Here's a short leg would be here. Because it's across from the 30-degree angle, that's got to be the short leg. The long leg is across from the 60-degree angle, so this is the long leg. And the hypotenuse is the only piece of information we've been given again. So if I was going to solve for either, let's put an x here and maybe a y here. If I was going to solve for x or y there, well, all I have to use is the hypotenuse. So I need to start with that fact. The hypotenuse equals the short leg times 2. Or 2 times the short leg. Okay, so the hypotenuse in our case is 7 square roots of 3. it equals 2 times the short leg, which is x. So now we're going to divide by 2 to get x alone. X equals, ooh, look at this. 7 doesn't divide nicely by 2, and you can't divide a square root by a non-square root, so we'd leave our answer as 7 square roots of 3 over 2. That's our x value. So now how do we find our y? Well, y is on the long leg. The formula for long leg says the long leg equals the short leg times the square root of 3. So the long leg y will equal our short leg, which we just found. That's this guy, 7 square roots of 3 over 2. So 7 square roots of 3 over 2 times another square root of 3. So that's like a square root of 3 over 1. Now we just need to do the math here to calculate this. So on the top of this fraction, if I multiply this, this would be 7 square roots of 9, because square root of 3 times square root of 3 makes square root of 9 over 2. So now continuing one more step, square root of 9 is 3. So this is like 7 times 3 over 2. So that's 21 over 2. So 21 halves essentially is what that y value would be. So sometimes we're just going to use the same formula, right? But sometimes the algebra leads us in a different path based on the information we have and also the side links we have. So I want to thank you for taking good notes today in this little geometry review. Like I said, we're going to be using these in our upcoming units, so it's very important that you understand your special right triangles and your Pythagorean theorem. Thank you. Kincaid out.